Hello dear students, welcome back to the lecture series on theory of semi-groups with course code MMTE 405. Now we are going to discuss the Green's equivalences. So first of all, we'll show that there are certain properties. We'll see that there are certain properties of the class of all equivalences and the class of all congruences on a given semigroup S. So let's discuss those properties first. So let S be a given semigroup. Let S be a given semigroup. And let's suppose that cursive C of S and E of S, cursive E of S, let this be the denotes the collection of or class of all congruences and equivalences on S. It's a collection of all congruences and collection of all equivalences on S respectively. Then these two collections are partially ordered sets. You can easily verify with respect to the inclusion relation. Then cursive C of S and cursive E of S are partially ordered sets, or they are partially ordered sets. They are partially ordered sets with respect to the inclusion relation. Okay, under inclusion relation. Inclusion relation. They are partially ordered sets. And in fact, they are actually lattices. So we'll see that they are actually lattices. Now, also for any rho and sigma in C of S or in E of S, then the intersection rho intersection sigma, it also belongs to C of S, or you can say their intersection, if they are in a E of S, then their intersection is also in E of S. E of S. So, and this is the greatest lower bound of rho and sigma. Rho and sigma. So therefore it contains its greatest lower bound. So also for any rho and sigma belongs to C of S or in E of S, their intersection is again in C of S if they are in C of S, and their intersection is in E of S if both the relations are in E of S. Now we see that means C of S is closed under greatest lower bound. It contains greatest lower bound of any two elements. So therefore C of S, or you can say A of S, contains, or you can say, let me use this notation, join. And then this and sigma, rho intersection sigma is the greatest lower bound of rho and sigma, respectively in C of S and E of S. So therefore the join of rho and sigma, it belongs to C of S. It is closed with respect to the sorry, it's meet, not join. Meet of this. So meet means the smallest congruence containing the congruence rho and sigma. That's obviously the intersection. Oh, sorry. You can see, therefore, this rho meet sigma, which is equal to rho intersection sigma. It belongs to C of S. Or you can say for the E of S, it's also true. Equal to rho intersection sigma, it also belongs to E of S. E of S. So it's closed with respect to the greatest lower bound actually. Now we'll see that it's also closed with respect to least upper bound actually. If rho comma sigma it belongs to E of S, then we know that rho union sigma E is the smallest equivalence containing rho and sigma. You can, this is already done actually. It's actually the smallest equivalence containing sigma, rho union sigma. So therefore it is also the smallest one containing rho and sigma. So therefore it's actually the least upper bound. Therefore rho union sigma E, it's actually the least upper bound. The least upper bound of these two belongs to, because it is the equivalence. It is the smallest equivalence containing rho and sigma. So it belongs to E of S. It belongs to E of S. Okay. So that means that this is closed with respect to least upper bound also. And similarly, if they are in C of S, cursive C of S, that means they are congruous. Then rho union sigma sharp is the smallest congruence containing rho and sigma. So that means rho union sigma sharp is equal to the join of rho and sigma. So in other words, we can say this C of S is also closed under this the least upper bound, because it contains the least upper bound of any two members of C of S. Now, if they are in rho sigma, they are in cursive C of S, then we know that rho union sigma sharp is the smallest congruence, containing rho and sigma. So therefore rho union sigma sharp is actually the meet of rho and sigma. And it is the congruence, so it belongs to C of S. So that's both E of S and C of S are leads. Okay? They are actually lead seeds. Now we'll see that this since rho and sigma, they are actually congruent. So now let's check this one. Now let's see this. This one is actually equal to rho union sigma sharp is actually by definition or by the theorem that you have already done in previous lectures. it's equal to rho union sigma C E. Okay, and that's equal to rho C union sigma C whole E, and that's it's equal to, what's rho C? It's the smallest compatible relation containing rho, but rho is itself compatible, therefore it's equal to rho, and this is equal to sigma because sigma is itself compatible, it's sigma power E. So in both the cases, the smallest congruence or smallest equivalence containing sigma, rho and sigma, it's actually sigma union rho E. In case of congruence, it was actually sharp, but we have seen that this is actually the same as in case of the equivalence relations. It's actually union E, rho union sigma E. Okay, yeah. Now we prove the following theorem. And the theorem is, let's prove this theorem. Let's prove this theorem. Let rho and sigma be equivalences. Let rho and sigma be equivalences. Equivalences on semigroup S or on a set S, okay, on a set, not necessarily semigroup, on a set S, or in case of congruences, they are on semigroup. Congruences on a semigroup S. On a semigroup S, okay. So if we prove the result for equivalences, then they are just equivalences on sets actually, not necessarily semigroup. But in case of congruence, it must be a semigroup here because there is a relationship between the equivalence relation and the binary operation on that semigroup S. So that compatible, that we already discussed it. Okay, so there are equivalences on a set S. In case they are congruent, then that set S actually it's a semigroup in that case. Then this pair, it belongs to the relation rho join sigma, means the smallest equivalence or smallest congruence containing rho and sigma, if and only if for some natural number n belongs to n, there exist elements, x1, x2 up to x2n minus 1 in S. They are in S, such that a x1 belongs to the first one, and x1, x2 belongs to sigma, and then x2, x3 belongs to rho, so on, and finally the first it's odd, x2n minus 1 comma b, so odd, it means it's in sigma. Okay, it's in sigma. So this is the result that we need to prove. Given two equivalences or given two congruences on a semigroup S, we say they are related to, they are in rho joint sigma, means the smallest congruence containing rho and sigma, if and only if for some natural number n there exist x1, x2 up to 1, x2n minus 1 in S, such that this holds. So in case suppose there exists a natural number n such that this holds, then a comma x1 comma x belongs to, so it's in the join, and now this is let's prove the direct part first. Suppose they are in this the join of rho and sigma. So to prove this theorem, to prove this theorem, we first show that this drive is actually equal to rho composition sigma infinity, and we know this infinity. It's actually the union of rho composition sigma power n runs from 1 to infinity. That's already discussed. So let us first prove this. Then we'll see that from this equation we can easily deduce this theorem, that if and only if. Okay, let's first prove this. So we know that what's this drive? It's actually the union E, both in case of equivalences and congruences. This is already proved, already verified, and that's equal to that's done in one of the previous lecture, that it's actually equal to this R. It's actually equal to R infinity, where this R is equal to, this is already done, it's equal to rho union sigma union its inverse union identity on S. Okay, this is already done. This is actually R or infinity, where R is equal to this. You can see one of my previous lecture in which we have seen that this R, if we want to find RE, that RE is actually R infinity. You can say R is equal to this. What we have done in that theorem, R is equal to this. So R is actually symmetric relation as well. It's a symmetric relation, and in that theorem we have seen that this RE for any relation R, it's not this relation, for any relation R, RE is equal to R union R inverse union identity on that semi-plus power infinity. This is done. You can see this theorem. So here R is this, so it's symmetric relation, so we don't need to write R union R inverse, we just write, and it also contains IS, because sigma rho contains I, sigma contains I, so we don't need to write it in case R is both symmetric as well as this, then this R infinity is same as this rho union sigma power E. It is the same. So let's try to find this. So actually this one. So if you want to write it precisely, so I will write it like this. It's equal to, by that theorem, it's equal to rho union sigma union rho union sigma inverse union identity on S power infinity. This actually, so it's actually R power infinity, where R is this relation. That's the smallest equivalence containing R is equal to R union R inverse, and union the identity relation. And if you see, this is equal to, you can see this is equal to rho union sigma, and this is rho inverse union sigma inverse union identity relation, because rho contains identity relation. It is an equivalence relation, so we don't need this I here. Or infinity. and that's equal to, and rho inverse is same as rho because rho is also symmetric. Sigma inverse is same as sigma, so it's just rho union sigma power infinity. Okay. Okay. So we have seen that the join of rho and sigma is equal to rho union sigma infinity. Now let's look at this. Now name it star here. This is an important relation. Now rho it's subset of rho union sigma, and sigma is also subset of rho union sigma. This is trivial. So which implies rho composition sigma is actually subset of rho union sigma whole square. To compose rho composition sigma is subset of rho union sigma composition of rho union sigma, that's square. So in general we can see that if you apply this n times, if you apply repeatedly this relation, rho composition sigma is subset of rho union sigma whole, if I apply rho composition sigma on both sides, and you will see that rho composition sigma square is subset of rho union sigma whole power 4. So this will also give rho composition sigma whole square is subset of rho union sigma power 4. This is simple, and in general we will see that in general it's rho composition sigma power n is subset of rho union sigma power 2n for all n greater or equal to 1, and you can see the union will be subset of this union, but this union is equal to power infinity. That's the notation, and this is again the power infinity, and that you have seen it's actually this one, it's equal to what? It's rho join sigma by star. By star. Okay. So this is the one inclusion. Now we prove the reverse inclusion. We need to show that rho composition sigma, rho join sigma is subset of rho composition sigma power infinity. To prove the reverse inclusion, to prove the reverse inclusion, we see that so notes that this is a rho